while Fred's getting that up, so Fred Sigworth is coming from Yale University. He has made a lot of contributions into the cryo field. He was one of the first people to propose using maximum likelihood methods for refinement. He's worked on ion channels and other methods of looking at them in a lipid vesicle. He also is part of the transformative high-resolution cryo program. He's one of the first round of curriculum development partners, and he's created a lot of material in cryo principles, and that's the website you can see. So whenever you're ready, Fred, you can take it away.
Okay. I'm assuming that you can hear me, and I really want to be interrupted with questions. So if someone can grab the mic and yell at me when the time comes, that would be good. Now, let's see, can you see my screen?
See your full screen.
I'm showing the wrong screen. Here we go. Okay, let me try this again. There we go. Okay, here we are.
Okay.
All right, so I'm going to do the impossible this morning, which is to tell you all about the foundational mathematics of leading up to 3D reconstruction, 3D classification, all that stuff. So I'm doing this in 3 parts, and this is the first part where I'm going to review complex numbers. I know a lot of you've had that in high school or whenever. And the big deal in this part of the lecture is how contrast happens in the electron microscope, how defocus contrast happens, and how we can model it. So complex numbers, you probably remember them, and the reason we talk about them is that the equations are simpler, they're good for Fourier transforms, and everyone's using them for getting magnitude and phase of structure factors. So a complex number is based on the imaginary unit I, and a complex number has some mixture of an imaginary part and a real part. And you can do all the operations you would want to do with complex numbers. And the thing that I really want to emphasize, because we're going to use it a lot, is this thing called the complex exponential. So you remember what e to the x is. So e is this transcendental number, and one way of representing e to the x is this Taylor series. And a really useful approximation when x is really small is just say, well, e to the x is approximately equal to 1 plus x. And we're going to use this approximation a lot. Now, the complex exponential is defined as a cosine function, which is the real part, and a sine function, which is the imaginary part. And so if you try to plot this thing, what we're going to do is we're going to plot imaginary versus real. If you plot it in 3D, you see the thing is a helix. And the helix has a periodicity of 2 pi radians, and it's circling around, the result is you're tracing around the unit circle repeatedly. Finally, any complex number can be represented 2 different ways. You can do what we just described, which is the real and imaginary part, and you do it in this complex plane, and there's our number. But another way of representing it is to say, well, there's an angle, a phase angle theta, and a magnitude, which is this radius r. And so you can represent it either in this Cartesian way or in this sort of polar coordinate way. that's all I'm going to say about complex numbers. Yeah. Any questions yet? No, you're probably all very happy or bored or something. All right, I'm going to increase the magnitude of your image on my screen so that I can see you better. Hang on. There we go. Hi, class. Okay, so now defocus contrast. So the useful contrast that we get when we image a cryo-EM specimen is phase contrast. Basically, when an electron wave passes near an atomic nucleus, it sees a positive potential, and that speeds up the electron briefly, and that shifts the phase so that the electron wave after it's passed by there is different in that it's been shifted in phase from the unscattered wave. And this is how we're going to make images, is make use of this phase shift. And the phase shift is really small. There's this interesting coefficient that says you get about 0.5 milliradian, so what's that, 1/16 of a degree of phase shift per volt angstrom of integrated potential. So what we do is we defocus the microscope in order to see our object. So as we change the amount of defocus, we get different looking representations of our original object. We defocus in a way that's called underfocus, and I'll tell you why later. And at high defocus, the high resolution information is strongly delocalized. But at high defocus, the low resolution information comes through much more strongly, and it's easier to say pick particles when you have lots of signal from using a high defocus. Now, image processing can relocalize the signals no matter how much you delocalize them, but at most only about half of the theoretical contrast is preserved by defocusing. That is, in principle, if you have a fancy device called a phase plate that I'll describe in a little while, you get twice as much contrast as defocus contrast. Now I'm gonna do a test specimen here, which is just a grating with 5 angstrom periodicity. Imagine a beta sheet or something. It has about that periodicity. And as we defocus, again, we see this thing where the contrast is coming and going, and also we have some delocalization of the signal from the object. And so we want to understand how it is that we get an image in the first place, and what's happening when we defocus. So electron waves, have short wavelengths. At 300 keV, it's about 2 picometers, but those electrons are going really fast. And physicists would write the wave function of an electron wave is this e to the ikz. Here's our complex exponential. It just says the electron wave is represented by one of these complex exponentials where it repeats every let's say 2 picometers. Now, if we insert a phase shifting object that slightly perturbs the phase, so this is my phase shifting object, then the electrons come in as nice plane waves, and they come out a little bit wiggly. Here you can see it better. Plane waves, they come out slightly wiggly, and so here's mathematically my object is going to be a grating. It's going to be cosine. It's a cosine function with a periodicity d, which is going to be 5 angstroms. And it's going to have a very small amplitude. So this is just a small perturbation of the phase. And so right after the object, we have the wave function is e to the I, and then this phase perturbation. Okay. Now, we make a very important approximation, which is called the weak phase approximation. So the perturbation is set by this number epsilon, which is really small. And then we make use of this of the approximation that I just talked about. You know, e to the x is about equal to 1 plus x. And so we can say that um, this complex exponential just becomes 1 plus whatever the exponential was. This is called the weak phase approximation, and it makes everything much simpler, and it's just exploiting the fact that we don't get a lot of phase shift of electrons going through most of our objects. So these two terms in the approximation have physical meanings. So this one means is the let's say the undiffracted wave that goes straight through, and this thing, this that has an imaginary amplitude, is the diffracted wave or diffracted waves. And in fact, for a grading, what we can say is here's the undiffracted wave, and there are two diffracted waves. You can kind of see them here. So here, the incident waves are coming down here, and then you see something going on where you see at a very fine, very weak angle, very small angle, you can imagine two different diffracted waves moving like that. And so if we now do the same trick of varying the defocus, that is, we're going to focus at different regions below the specimen, which is sitting right up here, we get varying amounts of contrast. There's a point here where there's no contrast, and then there's more contrast in the opposite direction. Now, how do we get contrast anyway? Well, what's happening is that the undiffracted wave is interfering with the diffracted waves, and the diffracted waves are moving at this small angle. It's very small because the sine of that angle is lambda over d. And so if we pick some point down here, what we're looking at as far as the intensity is, we're looking at the intensity of the undiffracted wave plus the diffracted waves that have come down from other locations on the object, and they interfere right here. So the point here is that the diffracted waves have a different path length. Okay, so the path length is longer by a small amount, which we'll call zeta, and here's a formula for it. And here's an example. So if we're using 300 keV electrons, and the grading is 5 angstroms, and if we sit here at 100 nanometers below the specimen, then the difference in path lengths is 0.8 picometers. It's about half an electron wavelength. So then if we define the phase difference between the undiffracted and the diffracted waves, that phase difference is just going to be 2 pi over lambda times this distance difference. And if we do this example, the phase difference is 0.8 pi. Okay, you like that? This is an important point. So shout out if you have a question. Okay, so the phase of the perturbation of this interference is a big deal because we're saying we have an undiffracted wave which we say has amplitude 1, and this is our complex plane, and so we say this is it has a real value of magnitude 1, so we're right here. And now if we add to it a diffracted wave that changes in this direction, that is, it contains, just has an amplitude of I, we're not going to change the magnitude of the result much at all. But if the perturbation is real, that is, it's not it's not imaginary, but it's real, then when we add epsilon, 1 plus epsilon, 1 minus epsilon, we actually get a difference in the magnitude. And that's how it's going to work. We want to have a difference in the intensity of the waves coming from our phase difference. And so we can't do it if we just leave the undifracted and diffracted waves as they are. We have to somehow get a phase shift such that the diffracted waves come out being real. Okay, so here's another part of the simulation. So this is what I showed you before, and if I really magnify this, yep, there are these little electron waves that are so tiny that we can't see. So what I'm going to do first is I'm going to unwrap this periodicity, and the way I will do it is I'm going to divide the actual wave function by the wave function by the unscattered wave function. And so what that does is instead of oscillating at this incredible rate of once every 2 picometers, it doesn't oscillate at all. Okay, so here is the undiffracted wave, and it's equal to 1, a real value. And now still we see this interference going on. Now the next trick is let's get rid of the undiffracted waves so we can see what those 2 diffracted waves are doing. So here they are, and you can see I've colored them according to phase, and you can see up here, yes, they're imaginary. We see blue and yellow. Blue and yellow meaning it has an imaginary amplitude, and here is red and green. That's what I want. It has a real amplitude, and we get interference at that point. And the interference is gives us then a variation in the intensity. Okay, is that cool? Somebody raise your hand and say that's cool. Nope. Okay. No way. Okay, so now you're not going to like this, but it turns out that everyone does under focus, which means that they're actually focusing the microscope above the specimen. So here's the level of our specimen. We've been talking about what happens below, but if we extrapolate the waves upward, we can then sort of mathematically say, well, if the specimen weren't there, but we were just looking at waves propagating in free space, we can ask, what would the waves be up above? And so we can do that mathematically, and we can do this trick where we say, okay, so suppose we do focus above the specimen. Well, we just get the nice continuation of this contrast. So here's the terminology. We usually, when we talk about the amount of defocus, when we take an image, we're always talking about focusing above the specimen. So I'm going to use delta for the amount of defocus, and z increases downward. So that's the definition of delta. We also talk about spatial frequency, which is 1 over the grading periodicity in this example. And the phase shift chi, which is the phase shift between those 2 waves, is proportional to the amount of defocus. And so the contrast transfer, that is how much contrast we get out of here from having a specimen phase grading here, is equal to the sine of this phase difference chi, and it's approximately this. Okay, so what we see here is that the amount of contrast varies as a sine function of the amount of defocus. But another way of looking at it is to say, let's pick one level of defocus and ask what the contrast is as a function of spatial frequency is a function of the grading periodicity. And you know it's going to change because as we change the grading periodicity, we're going to change the angles between those two diffracted waves, and so we're going to have a different periodicity of maxima and minima in the signal. And in fact, this is what it looks like. Here's chi. Chi varies as the spatial frequency squared. And so when we do the sine function of the spatial frequency squared, we get this accelerating sinusoidal variation. Now, we usually use defocus values on the order of a micron, maybe a bit more, maybe a bit less. And when you think about it, a micron of defocus, if we are defocusing a whole micron, a whole 10,000 angstroms above the specimen, that's a really long distance. It's, 500,000 wavelengths because the electron wavelength is so short. And this has big ramifications. We're actually relying on the fact that in a good microscope with high coherence, electrons take exactly the same path through the column. They don't come through at different angles. And the reason that's important is that we're imaging what amounts to an interference pattern 500,000 wavelengths away from the object itself. And if electrons come through at different angles, they are the all important interference pattern is going to be washed out. So that's why we spend an extra $1 million to have high coherence electron sources, field emission sources. Okay, so let's talk about delocalization for a minute. So we know this angle theta, which is between the undiffracted and the diffracted waves, and we're going to defocus this distance delta above the specimen. And so we can ask, well, how far away is the relevant diffracted wave from the undiffracted wave? Well, that's just geometry, and we can work it out. And by a small angle approximation, it's just delta lambda times S. I apologize. S is now spatial frequency, starting with this slide. And so if we do an example, 3 micron defocus and 3 angstrom resolution, then the amount of delocalization is 200 angstroms. So that would say that if we really wanted to use that much defocus, we actually ought to leave a border of 200 angstroms around our object. This doesn't quite work. This is from the famous TRIP-V TRIP-V1 data set from Yifan Cheng's lab, and this is the size of the box that they use to box out their particle images. And the box looks like it's really big, but it is not quite big enough to actually contain all of the delocalized information at such a high level of defocus. Less defocus, less delocalization. Most of their images were below 3 microns. Okay, so do you like that? So this is our first sort of practical tip here, is that you can estimate how big the box needs to be around your particle image to include all of the delocalized information. Okay, so let's do some more details about the contrast transfer function. Are we okay, guys? I need a smile or a wave or something. Good, thank you. Okay, so now let's think about what happens when what happens in the microscope, because we want to know what's actually happening down here at the camera where we're taking pictures. So here's a lens. The lens focuses the undiffracted beam down to a point, and then it spreads out again. And so down here we have undiffracted beam, and here are two diffracted beams, and we have the same relationship of phase differences and so on down here as is happening up here at the specimen. But notice that now we have what would be the extrapolation of the wave fronts up above the specimen here, magnified down here at the camera. And so that means that when we do underfocus, we can actually be looking above the specimen, so to speak. So underfocus means that the actual focal plane, the conjugate plane for the specimen, is down below the camera, and the conjugate plane for where the camera is above the specimen. So that's what I mean by under focus. We're looking above the specimen. Now we're going to start looking at embellishments to the contrast transfer function. So the first one is spherical aberration. And spherical aberration, it's a terrible name. It just comes from the fact that in glass lenses, if you make a glass lens out of with spherical surfaces, then at high angles, the lens focuses more strongly than at low angles. And so we can say that the spherical aberration changes the defocus, makes it smaller, uh, in a way that goes as the spatial frequency squared. So it goes as the size of the angle, size of this diffraction angle squared. So what we have to do is now what we have to include not only our regular defocus, but this modified defocus delta prime. And if we go and work it out, it looks like this. So here is the original defocus term. Depends on the wavelength, depends on the amount of defocus and on the spatial frequency. And then here's a new term that depends on the spherical aberration coefficient, the wavelength, and the frequency. Doesn't depend on the defocus, but it has this really steep frequency dependence, s to the fourth. And if you go and work it out, it turns out that the coefficient that we have in our microscopes, that's around 2 millimeters, means that this term becomes important only at fairly high, well, I don't know if you call this high resolution anymore. You have to worry about it above about 4 angstrom resolution. The other thing is that now and then an electron passes really, really close to an atomic nucleus, and it gets scattered through a really high angle. And if you are using an objective aperture, those electrons get lost. And so we get a little bit of negative contrast from high angle scattering. This means that we have a little bit of amplitude contrast even in the absence of any defocus. And I like to put it in my formula here. I say the amount of amplitude contrast is this small angle alpha, but other people take it outside of the CTF formula and just say, well, the CTF is all these terms, and then we do minus alpha as the amplitude contrast term. Okay, so here's the plain vanilla defocus contrast transfer function. That's what chi looks like. There's the accelerating sinusoid. And now when we add these other terms, look what happens. So here's alpha. This is the amplitude contrast term. It means that we start out with a tiny bit of contrast at 0 spatial frequency thanks to that. And then at high spatial frequency, we have the effect of the the CS term that actually starts to reverse and is actually going to make the chi function start to move in the other direction. So altogether, this is then what the CTF looks like. It's non-zero. It oscillates, and then the oscillations actually switch in direction and start oscillating rapidly in the other direction. So that's what the spherical aberration does to us. And here's our 4 angstrom effective spatial frequency. So the spatial frequency in inverse angstrom. So here's the point where I would say that CS starts to take effect. And see, when we get down to 2 angstrom resolution, the CS, the spherical aberration is getting to be really important. Okay, so now why do we use under focus? Well, the reason for doing under focus is that makes the defocus part of the CTF start off going in the negative direction. And that's just what we want, because the amplitude contrast is also in the negative direction. Where there is stuff there in the specimen, the image looks dark. And where there's stuff in the specimen, the image is dark because of the amplitude contrast, and also it's also because of the defocus contrast. So we have those both taking off in the same direction, and the amplitude contrast helps us in that respect. Now, the people who do material science, who at least in the old days, they didn't like to do computer processing of their images. But what they would do is they would defocus the microscope just a little bit, just enough so that you had a nice spatial frequency range where the contrast was uniformly negative, it turns out. And they do that by making the chi function kind of flat. And so they pick a small amount of defocus so that you really get pretty good looking images without any computer processing of the images. And this is called Scherzer defocus. This guy Scherzer said this is a good place to do the focusing, but we don't like it. And the reason we don't like it is that the amount of contrast transfer at the low spatial frequencies, which are the ones that are going to allow us to actually see where our particle is, that amount of contrast is pretty low. Okay, so that's the simple version, and just for you math jocks, I just wanted to put in the math of how the interference works. So here is our here is our wave function, undiffracted and diffracted, and quantum mechanics tells us that the intensity is the magnitude squared of the wave function, and that's going to be the real part squared and the imaginary part squared. And so if you work through all this stuff, the real part squared is this 1 plus 2 sine of chi times the original phase object, plus a couple terms that are of the order of epsilon squared. And because epsilon is already a small number, epsilon is a really small number, and so we can ignore those. So we just say, okay, the intensity under the weak phase approximation is just going to look like this. We're going to ignore this 1 that just says that's the constant background intensity. And so the intensity is going to change with this sine chi multiplier. People also throw away the factor 2 for some reason. Well, people aren't doing really quantitative imaging anyway. And so we just say that the contrast transfer function is the change in intensity per unit change in electron phase, and it just goes as sine of chi. Okay. All right. Finally, the phase plate. So the phase plate is really wonderful device. The idea is, we have this problem that when we're in focus, there's no interference between the diffracted and the undiffracted wave. So what you do is you insert this device that maybe doesn't shift the diffracted rays, but shifts the phase of the undiffracted wave by some amount, say 90 degrees. If we shift it by 90 degrees, then the CTF becomes a cosine function. Okay, and you'll remember cosine of 0 is 1. That is, this is going to be a CTF that starts out, instead of starting out essentially at 0, like the sine function, is starting out at 1, like a cosine function. And this gives really awesome looking images. You can see, you can really see your molecules a whole lot better than you can in defocus contrast. And so this is minus CTF plotted as a function of spatial frequency, and so this cosine CTF is perfectly flat until spherical aberration takes over and it starts to oscillate. But the point of this graph, and this is work by Rado Danev, the point of this graph is that your microscope has to be really, really carefully focused in order to make this work, because if you're off by 60 nanometers in the amount of focus, that's about as far off as you can get and still able to get something like 4 angstrom resolution. So we're actually really lucky that we can estimate the amount of defocus very precisely just from looking at a micrograph. But if you take an in-focus picture with a phase plate, it turns out that it's very hard to determine what the amount of defocus was, and so this is technically a lot harder than you might imagine to acquire data this way. Okay, so we can just look at a micrograph and see what the amount of defocus is, and the way we do that is we compute what's called a power spectrum. So if you have a micrograph that has some stuff in it, and you take the power spectrum, which is the magnitude squared of the Fourier transform, what you see is this oscillating bright and dark rings. And the dark rings are the zeros of the contrast transfer function. So if we just looked along here, and if we were to plot that, that would just look like the square of the CTF. Now, in this representation, each pixel in this plane represents, in effect, the signal from a grating. So if I start looking at points displaced from the origin, as I move farther from the origin, I get finer and finer gratings. The direction I move in this plane tells me the direction in which the grating is oriented, and so this representation in this spatial frequency plane is really quite useful if we're thinking about gratings and we're thinking about spatial frequencies. And this brings us to Fourier transforms, which is going to be the next part of my lectures. So while I'm changing slides, please, somebody asked me a question.
A couple of questions. When you walk.
Yeah.
Hi, Fred. Thanks for the great seminar this morning. I have a question that's kind of been plaguing me for a while now about spherical aberration. So you're saying it's important for essentially any kind of reconstructions below 4 angstroms, or at least signals that are below 4 angstroms.
Yeah.
So does that mean when you're reconstructing something underneath, let's say you're aiming for like 3.5 angstroms, does that measurement of spherical aberration in that microscope become essential? Like, do you have to be very, very accurate with that measurement? And how do you measure it?
Right. So measuring it is non-trivial, and almost you can, for all practical purposes, just rely on the value that your service engineer gave you, or the manufacturer told you what the value of CS is. So it's basically a property of the exact geometry of the magnets that form the objective lens. So I think people doing anything but the very highest resolution sub-angstrom kind of reconstruction can just use the manufacturer's value. So CS is important, but it's important just that you have to include that term in your CTF, and of course all the software knows to do that. I think you give CS, for example, when you first import images into Reliant, at least.
Yes. Okay, thanks, Fred.
Hi, I just wanted to go back to the section about defocus.
Yeah.
So one thing that we know is that at at very close to focus, you get very little contrast at the lower spatial frequencies. And
Right.
looking at the equation for the CTF, I think that makes sense. You can just clearly see the graph. But
Yeah.
I'm having trouble connecting that to a more intuitive understanding of why that happens. Like, what's the physical reason for why you get such little contrast at low spatial frequencies?
Yeah. So let's see. We'll see. We'll see in the next lecture. No, we'll see next hour that your typical object, macromolecule, has a whole lot more signal in the low spatial frequencies than in the high spatial frequencies. And so that means, as far as being able to see your macromolecule, high defocus is better. See it by eye. Now, as far as getting the really high resolution information, you can get that just fine at really low defocus. But and I'll just go put that picture back up here. Yeah, okay, you got my whole screen there. But so at zero defocus, you actually do get a little bit of signal, and that's just from the residual of the spherical aberration. But anyway, does that answer your question?
So I guess I want a more of a more physical reason for why you get low contrast at higher spatial frequencies. Just what's happening in the microscope or to the electron rays to make that contrast not visible.
Yeah. So what's happening is this. Let's see. The amount of defocus sets how rapidly there is this phase shifting and this alternation between all imaginary and all real phases for the diffracted rays. So the lower the defocus, the longer this periodicity. And so if you go to no defocus, then basically the diffracted rays stay imaginary pretty much the whole way down. Or no, here's what we do. I'm sorry. Low defocus means that we are picking off the interference right here, very close to the specimen, and that means that we have no interference until we get to pretty high spatial frequencies. That's the way to think about it. Is that helpful?
Yes, I think that does help. Then just the other thing was trying to relate this to traditional light microscopes. So on light microscopes, we try to be at focus as much as possible. So what's different with electron microscopes that we want to be at? What would be that fundamental difference between light microscopes and electron microscopes to make the focus value different?
Well, we have the same problem with with light microscopes. It's just that light microscopes have nice phase contrast devices. They have phase plates and they have Nomarski interference optics and so on. So they've solved the phase contrast problem by having the right kind of optical components. And it's just been really hard to make the right optical components for electron microscopes. So if you have just a plain bright field microscope and you're trying to look at, say, a cultured cell that's basically transparent, it's just a phase object, you won't see anything until you throw the light microscope out of focus.
Okay, thank you.
Yeah.
One more question, Fred.
Yeah.
Hi, Fred. I just got a quick question about faceplates. In practice, what are the pros and cons of using faceplates?
So the pro is, of course, you get this wonderful large amount of low frequency information. And I think the practical way to use a faceplate is to use it with defocus. If you defocus it some, then you get those wonderful rings. They're called tone rings in the power spectrum, and you can estimate very precisely what the level of focus is. So then the advantage is just that you have extra signal at really low frequencies. That means faceplate is really great for doing tomography, where you're really interested in low frequency information. Now, everyone thought that faceplates were going to give us better results, but Rado Danev did some careful measurements and decided that at high spatial frequencies, the fact that there's a device there in the electron beam, happens to be an amorphous carbon film, perturbs the high spatial frequency information and reduces the amount of signal there. So in the end, single particle people don't like faceplates. It might be interesting if you have an extremely challenging small molecule where just localizing it is important, but I think no one's using faceplates for single particle.
Okay, thank you.
Not clear. Yeah.
Okay, take it away, Fred.
Okay, let's see how you're ready to sit through another one of these sections. Here we go, and this is now my part 1B. Okay, hopefully you can see that. Okay, so this is our Fourier transform. This is our Fourier transform scene. Okay, so Fourier transforms are based on the idea that you take any kind of function, any kind of signal, and you can reproduce it by summing together sinusoidal function sine waves. So for example, what I just showed you is I can reproduce a Gaussian function by adding together, looks 1, 2, 3, 4, pretty well by adding together six cosine waves, and if I added some more, I could make the approximation even better. And so the Fourier transform makes use of the fact that you give me any function, and I can reproduce it. The only trick is I have to know what are these coefficients that I have to multiply each of these cosine waves by to get them to sum to reproduce the original function. And the way I get those coefficients is through this operation called the Fourier transform. So if I have my Gaussian function and I give it to my computer and ask what is the Fourier transform, then out comes another function that I'll call g of u. So this is a function of spatial frequency, and the values of this output, these are actually the values I use to scale the cosine functions that I showed you before. So the Fourier transform just tells us the sizes of the coefficients, but because I can reproduce any kind of reasonable function by summing together cosine and sine functions, if I have the coefficients, that contains exactly the same information as the original function. So that's the cool thing about the Fourier transform. It just tells us coefficients, but it contains all the information. And it turns out that that the Fourier transform is a sort of interesting integral. You take your original function, you multiply it by, yes, a complex exponential that's the product of the original spatial variable and the frequency variable, and you integrate it all up and you get something that has no spatial information in it at all. It's just frequency information. So here's another one. This is a more challenging function to do a Fourier transform. You take something with a sharp-edged pulse, and you start adding together cosine functions. And as we add together the cosine functions, first it's kind of interesting that because the particular form I picked every other coefficient is 0. And the other thing is the coefficients are alternating in sign, and this thing does not converge quickly at all. The Gaussian function converged really quickly, but this one didn't. And if we go and ask a computer what the Fourier transform is, we get this horrible looking function that's sine pi u divided by pi u. U is the spatial frequency. It's also known as the sinc function, and it's horrible because it decays very slowly. It decays as 1 over u, and is infamous for having all of these ripples. So what do we learn from this? Well, there's this general principle that if you have something that is sharp in your starting function, the Fourier transform is going to give you lots of ripples. But still, this still works. You ask the computer to give you the coefficients, and you can then reproduce the original function. And in this case, you want to use more coefficients to try to get a better approximation. What we have just seen is that if I give you this Gaussian function, the Fourier transform happens to be a Gaussian function. If I give this rectangular pulse, I get this sinc function. This is another interesting one, a delta function, which is just a spike, turns into a constant in the frequency domain. And Fourier transforms have all kinds of interesting properties that I'm not going to tell you because we only care about a couple properties. One of the most important is convolution. Now, convolution is a filtering operation. What we do is we say, let's suppose that we have a signal that I'll call a G, and we have a kernel called H. And what we're going to do is to get every output point, we're going to look in the vicinity of output point at value X. We're going to look at the vicinity of G perturbed by S, and we're going to multiply it by the magnitude of the kernel at that value of S, and we're going to add it all up. So what that means is, here's the output of the convolution. And so, for example, if I want to compute the value of the output at this value, I'm going to look at the neighborhood of that value in the input signal, and I'm going to weight it by the magnitude of this kernel. So the net result is that I'm doing a smoothing operation because I'm taking multiple points of the input, weighting it by this kernel, and out comes something that's smoother. You see that? So this is what convolution is, and it's exactly what happens when a microscope looks at an object. You might say, well, the object has lots of ripples in it, but the microscope has a point spread function that is broad, and so what you really get is some kind of smooth version. Or in an old-fashioned hi-fi system, you have a treble control, and if you turn the treble control down, you're in effect convolving the signal that represents the sounds with a kernel that's broad. Okay, so it turns out that Fourier transforms are really cool because because of this property, that convolution of two functions is represented in the Fourier domain as just the product of the two Fourier transforms. And that turns out to be really useful. It's vastly faster to do the Fourier transform, multiply the two functions together, and transform back to do this convolution operation. That's because the Fourier transform on the computer is really, really fast, thanks to a really nice algorithm. Now, the other thing is, if in the Fourier domain, it's just the product of the Fourier transforms of the two functions, shouldn't we be able to take this filtered, this smooth signal and work back to that one? All we would have to do is divide by h of u. So we take the result, we divide it by h of u, and get some kind of g back. So that's a deconvolution operation, and doesn't always work well. So here's our filtered signal. In orange here, I show the unfiltered signal, and so we try to do 1 over h of u, and h is big H of u is a very narrow thing. You do the deconvolution, and it works kind of well, but this sharp pulse blows up. So anyway, deconvolution doesn't always work, but it's a really cool idea that you could make use of this property of Fourier transforms to try to do it. And we'll be talking about that in removing the CTF in a few minutes. Okay, so in 2 dimensions, which is where we use Fourier transforms in image processing, it's the same kind of idea. So we build up. We have a function, and we can build up a duplicate of it by using coefficients, which I'm displaying here as grayscale, and gratings. So what I'm showing here is coefficients of gratings of various periodicities, various spatial frequencies. And in this case, I have to fill in gratings going vertically, horizontally, and diagonally, and that's why I have this 2-dimensional array of coefficients. But once I added together some number here, what is it, about 12, about 12 different gratings, I can reproduce the original function quite well. Okay, so it's the same idea. We are reproducing the original function by adding together sinusoidal components. And in case you like this stuff, it's exactly the same formula, except that now we have x and y in it, and we have u and v in it. So u and v are the 2 frequency variables, x and y are the 2 spatial variables. And it has the same kind of properties, but there again, I'm sparing you most of the Fourier transform lecture because there are only a few properties that we really care about. One is convolution, again, another is rotation, and another is projection. So let me talk about these 3 properties of the 2D Fourier transform. So convolution in 2D is, again, just like convolution in 1D. I have a kernel, and I have the original signal, and out comes the convolution. And so here's an example. You have a light microscope and you have an object like that. Your light microscope might have a point spread function that looks like that. And then here's the image that you get. In the image you get at any point of the image is going to be the neighborhood of the points on the actual object weighted by this kernel. And you can see how the Fourier transform approach works. So this is the Fourier transform of my smiley face image. It's in color because the different colors represent different phases. We'll talk about that in a little bit. This is the Fourier transform of this Gaussian kernel, and this is the product of the two. So when I make the product, what happens is that the farther out points, that is the higher spatial frequency points, are set to 0 because they're 0 in the kernel. When I transform back, then I get my convolved object. So it's almost easier to imagine what's happening in the Fourier transform of the image than in the actual part of the image, and it goes vastly more quickly on a computer, which is why when people write reconstruction programs and so on, they're often switching between Fourier space and real space, whichever is quicker. Now, here goes the effect of the contrast transfer function. Let's suppose that we had a random object and we want to operate on it with the contrast transfer function of an electron microscope in phase and defocus contrast. Well, here's a representation of the CTF in 2 dimensions. The colors are such that red is positive and blue is negative, and so this is our familiar oscillating negative, positive contrast transfer function. This turns into a point spread function that's sort of complicated, and nobody thinks about that because it's so much simpler to do the Fourier trick. So what we do is we have our random object, we take its Fourier transform, which also looks like a random object. We have the contrast transfer function, we take the product of the two, and this is what we get. We get the beautiful colored random phases, and there are zeros here, which are the zeros of the CTF. Now, if I transform back, this is what my image would look like under phase contrast imaging, and you can see it's kind of gotten this rough, ripply kind of look, which is what it looks like if you look at a carbon film in the electron microscope. Now, there's one other thing you can do, which is instead of actually looking at the Fourier transform, this y tilde, we compute the magnitude squared of the y tilde, and so that gets rid of all the colors. This is the image that you see on the computer for your electron microscope that shows these dark tone rings. And gives you an idea of what the CTF looks like. So this is the power spectrum that I was talking about before. So the contrast transfer function of an electron microscope is most easily described in the frequency domain, and so what everyone does is follows this path to simulate an image in the electron microscope. There are other cute things you can do with convolution. For example, crystallography is best understood, I think, as a convolution. You have an object, you have a kernel, which is a lattice. If you convolve them, you get your object repeated in a lattice, but the Fourier transform of that is just the product of this and that. So if you take the continuous transform and you sample it at discrete points, and you do the inverse Fourier transform, you get a lattice of your original object. And if you pick the wrong lattice, you get overlap. You get what's called aliasing from not sampling the original transform finely enough. Okay, so there are two other properties that are really cool and that we use in 3D reconstruction. One is the rotation property, and that just makes use of the fact that in the exponent we have what looks like the dot product between x, the spatial variables, and u, the frequency variables, and so a dot product is invariant under rotations. And that, in fact, is what happens. So if you rotate the smiley face, you rotate its Fourier transform. So rotation of real space turns to rotation in Fourier space. And then finally, there's the projection theorem. So we're taking a CAT scan of your body, right? And so the way the CAT scan machine does is it sprays. This is a slice of your body, and the CAT scan machine sprays X-rays along in one direction, and a detector gives you a one-dimensional projection of your density. Now the trick is that if you take, you can also think about this 2D density of a slice of your body as some Fourier transform function. Now the cute thing is that the Fourier transform of this 1D projection turns out to have exactly the same values as the value of this Fourier transform along a single line, along a single slice. The way this works is a projection is an integral. So, for example, a projection along y is just an integral over the y variable, and the Fourier transform is an integral too. And it turns out that we can just convert part of this integral into a projection by just saying, okay, let's look at the 2D Fourier transform with the v, the second frequency variable, being 0. So this is exactly, if you work this out, the 1D Fourier transform of the projection of that function. Now the rotation property says that we can rotate u as we're taking these 1D projections, and as we rotate u, we're in effect rotating this thing, and that is the same as inserting slices at various angles. And if we insert enough of these slices, then we can actually reconstruct that, and we can do an inverse transform, and we can get the result of your CAT scan. So that is that's how you can do a 2D reconstruction. We'll talk more about this in a little bit. Now, the discrete Fourier transform is what's calculated on a computer. So this is the beautiful continuous mathematical object, and this is what happens on a computer, which is that we just replace the integrals with sums, and otherwise it looks pretty much the same. And so this is what the discrete Fourier transform looks like. It takes an image, let's say, of 32 by 32 pixels, and it converts it into another representation, which is also 32 by 32 pixels, but the quantity at every pixel has an amplitude and a phase. It's a complex number. And immediately you should say, well, Gee, a complex number has two parts. It has a real and an imaginary part, and so there must be twice as much information here as there. There's something wrong. Well, it turns out that the real part and the imaginary part are each centrosymmetric. The real part is even, and the imaginary part is odd, and so there is a more efficient representation that where you could say, well, this thing is actually the same as 32 by 32 array of real values, but mathematically it's easier to let them be complex. So there isn't any trick, there isn't any gain of information.
Fred, you're breaking up. I don't know if that's internet on our side or your side.
Hello, test, is that? Am I?
Okay, we can hear you. Am I coming in clear or am I choppy as well?
No, you're coming in perfectly clear. Okay. Well, I haven't gotten any warnings from Zoom yet. Tell me if it's continuing. I can switch to a different internet, a different Wi-Fi.
Okay. We'll plow ahead.
We'll plow ahead. Okay, so now the scaling of the discrete Fourier transform is important to note. The issue is what is the size of a pixel in the Fourier representation of an image? And this is something that's going to come up in real life. Let's say this is a micrograph, and this is its Fourier transform, and you want to know, okay, so what's the maximum resolution that I can get out of this micrograph? And the easy way to do that is to say, well, what is the maximum spatial frequency that's represented by the Fourier transform? So here's how it works. We say dx and du are the pixel sizes of the two representations.
You're breaking up. I'm wondering, what is your microphone? Are you using AirPods?
I'm using AirPods, and I'm going to switch to the other AirPod.
We're also checking on our side because
yeah. Okay, let's see if it was a dead AirPod. So the question is, what is the size of a pixel here, and what does that tell us about the resolution? So the size of a pixel, du, is equal to 1 over n dx. That is, the size of a pixel here corresponds to the entire width of the original object. That is, the very first, as you move from one pixel to another, you're increasing the frequency of the grading by one cycle per the entire width of the object. Now, what about this? What about well, this is zero frequency in the center, and this is high frequency over here on the edge. N of the frequency pixels, n over 2 of the frequency pixels. So what is that? Well, this frequency here, well, the entire width, n du, corresponds to 1 over dx. So half of this corresponds to 2 pixels there. The conclusion is that if we say that 1 over dx is, we'll call it the sampling frequency, that sampling frequency is twice the maximum accessible frequency, which is n du over 2. So let's do for example, let's suppose that this is our micrograph, and at the magnification we're using and so on, 1 pixel is 1 angstrom. The edge of the Fourier transform here is a spatial frequency of 0.5 per angstrom. That is, it represents a resolution of 2 angstroms. And this is a representation of the all-important sampling theorem that says that the highest frequency that you can recover from a sampled image is half of the sampling frequency. This is the Nyquist theorem, and people will say, well, the Nyquist frequency is the edge here, and the Nyquist frequency is always half of the sampling frequency. So anyway, so that's what this scaling is, and that's useful because you're looking at DFTs all the time when you're looking at Fourier transforms of images. Okay, so that's the end of this part, and I think we're all ready for a break. Okay, so for the last act today, I'm going to talk about single particle reconstruction. And let me first talk about a simple topic, which is conventional correlation-based particle picking. So we're gonna make use of these properties of Fourier transforms again. I already talked about convolution. Correlation is really similar, and in fact, in Fourier domain, it's just the product of the two transforms, with one of them being the complex conjugate. The conjugate is something that kind of reverses time or space. So convolution looked like that. Correlation looks like that. And correlation basically says if S and T are the translations that superimpose G on top of H, then there's a maximum of the correlation. There's a maximum of the correlation function. So here's an example. Here's a reference, and let's say this is the signal. And if I compute this correlation, what I get is two really beautiful peaks, which represent the locations of the original object. And the reason this is interesting is it still works when the signal to noise ratio is horrible. So here's the same problem, but here you can hardly see the smiley faces in the signal, but we get clear cross correlation peaks. So that of course is exploited in particle picking. So here's an example of a particle picker I wrote. We have a whole bunch of projections of a 3D object, and I also made some decoy objects so that it will try to find the objects and try to find the decoys. So here is the maximum of the correlations with the decoy references. Here's the maximum of the correlations with the real particle references, and you can see there are places that look like bright spots, and those are going to be the locations of particles, and so you can use those locations as putative picked particles. And it's kind of cute. You can, in principle, go back and ask, well, which of those references fit it best at each of those locations. So that's an example of a simple particle picker, and it's done by this operation correlation, which is really similar to convolution, and it's vastly accelerated by Fourier transforms. Okay, so let's go on to the single particle reconstruction issue, and I wanted to talk about reconstruction. And again, I'm just going to talk about reconstruction of a 2D object from 1D projections because it's readily generalized. So we start out with the idea that there's a Fourier transform of any image, And as I was saying last hour, so we compute a 1D projection. We take that projection, we Fourier transform it, and we insert it as a slice into a 2D field. And just for fun, as we build this up, I'm doing an inverse Fourier transform of that, so we can see how well we're doing with reconstruction. So the idea is then we take projections at slightly different angles, and we start filling in more and more slices in the 2D field. Then we can fill in lots of slices, and you can see at this point, well, we have kind of a so-so reconstruction. The resolution is good in this direction, but not in that direction. And this is exactly the missing wedge problem, right? Because we're missing half of the signal in the Fourier domain, and we have these two wedges where there's no signal at all, and that gives us a kind of poor reconstruction. But if we fill in the entire field, we get a pretty good reconstruction. And if I had taken smaller angular increments, we wouldn't even have artifacts around the edge. So this is reconstruction by doing insertion of a Fourier slice into the higher dimensional field. And this is exactly how it works in 3D too. So you take a 3D object, compute a 2D projection, or get one in your microscope, compute its transform, insert it as a slice in a 3D volume, and if you insert enough slices, then you've covered the whole 3D volume and you get your 3D reconstruction. So the only problem with this operation in 2D or 3D is you have to know the angles. You have to know where to insert your slice in the higher dimensional volume. And that's the biggest trick, I think, in 3D single particle reconstruction. So how do you find the angles? Well, so here's here's an example from this famous data set. Here's one particle image. This is what I think the original particle looked like. This is what the original particle looks like when modified by the CTF. And so the idea is, does this match that? Or did I get the orientation wrong? So the way to do that is we do a comparison. We're going to compare our particle image with many different test projections of our 3D object. So I'm now plotting, this is a probability function as a function of two angles. This is the tilt angle, and the horizontal you can't see is the rotation angle, azimuth angle. And so as we compare this, as we compare our particle image with these various references, we can see that there is in fact a maximum in the angles, and the maximum is really pretty small. It's you can see that it's a peak that's only a couple degrees wide, and that turns out to be just enough to be able to do a 3-point-something angstrom reconstruction, which is what Yifan Cheng and colleagues got from this B1 channel. So even though it looks hopeless, there's enough signal there to be able to determine the orientations of the object pretty well. So we make a model of how an experimental particle image is formed. We say that we have a volume. We take a projection along a direction phi sub I and operate on it by the CTF, and we add a whole bunch of noise to it. So this is our model of what one of these individual particle images is. And what we want to do, of course, is we want to discover what is the volume that is projected and winds up in the particle image. And of course, the first step that we have to do is we have to figure out the orientation angles to start with. Now, to do this, we want to compare an experimental image with a reference. And for example, we can look at the pixel by pixel squared difference between the experimental image and the reference. We can look at the correlation like I just did, which is pixel by pixel multiplying the experimental image by the reference. And then there's a fancier way of doing the correlation called the correlation coefficient, which is sort of a normalized correlation coefficient, where you do the correlation and you normalize it by the product of the magnitudes of the image and the reference. This is nice because its maximum is supposed to be 1, whereas this one's maximum depends on just how much signal there happens to be at that place in the images. So to think about how we're going to do reconstruction, I want to start with a 2D problem, which is let's reconstruct just a 2D image from a bunch of noisy copies. So so we know how this is going to work. We say that the image is contrast transfer function operating on the true image plus added noise. And so let's suppose that this is the true image. There's its Fourier transform. There is the CTF. We multiply those two and we get this thing. And if we then transform back, we see the image is modified by the CTF. And just for fun, I'm showing you a slice through the CTF. The 1D contrast transfer function is a slice through the CTF. And it's our usual oscillating sinusoid, but it's decaying as you get to higher spatial frequencies. And that, of course, is due to the unavoidable blurring in the microscope. Just for fun, this is the point spread function. That is the Fourier transform of the CTF, but no one uses that. We all use this. Okay, so that's our model of how to get an experimental image. And again, what we'd really like to do is to just do a deconvolution. Let's just take our experimental image, divide it by the pixel by pixel by the contrast transfer function, and we could get back then some estimate of the original object. So that's how we would deconvolve the CTF. But of course, that isn't going to work. And the reason it's not going to work is that there are zeros in the CTF, which means that there are spatial frequencies where there is no information. There's going to be no information in the experimental image to work with. Okay, so how are we going to do this? So one way to do it is to get rid of the horrible fact that the contrast alternates at various spatial frequencies. So an old trick is to convert it so that the CTF in effect is always operates in one direction. It's called phase flipping. And so what we do is we just take the contrast transfer function and flip the phase. So this is -1 + 1 -1 + 1. We just multiply the CTF by those numbers. And what it means is we take an experimental image. And we can take an experimental image and multiply this by this function that is -1 + 1, and that will flip the phase of the underlying CTF. And that actually makes things look a lot better. There's less delocalization. Then there's a fancier way to do it, and that is called the Wiener filter. So remember, what we'd like to do is to do x divided by c. and that won't work. So Norbert Wiener said, what you can do is you can do c times x divided by c squared, and you can add in a constant, a regularization constant that keeps things from blowing up. So you pick this so-called Wiener constant, and then you compute this thing. Now, what does that do? Well, what it does is it converts the CTF into something that's a little bit broader. It still has zeros, but the zeros aren't as deep. And you get an even better looking reconstruction from if you operate on in effect by this CTF, you get a better looking image. But what we really want to do is we want to recover the original object from really noisy images. So here's what happens if you took that object. Here's at 1 micron defocus, at 2 microns defocus. You can see why 2 microns defocus is nicer, because you can see those low frequency components better. You can see the object better. So what you can do is you do a Wiener filter with an optimum choice of this Wiener constant, and you kind of recover the original object from a single image. But let's try combining information from multiple images. So in that case, here's what the Wiener filter looks like. We sum together contrast transfer function times an image, and we do the same thing in the denominator. We sum up the CTF squared, and we have an appropriate Wiener constant. And as we add together more and more of these images contributions, we get a nicer and nicer reconstruction of the original. It's not perfect, but we're definitely getting there. Now, there's a more sophisticated way of doing the Wiener filter, and this is what Norbert Wiener originally proposed, which is instead of this regularization value being a constant, we let it be the noise to signal ratio. It's the 1 over SNR. And now if we add together multiple images, we actually get a really nice restoration of the original object. Now, how does this work? Well, so what we're doing then, of course, there's our Wiener constant that's not a constant anymore, and here is this term CTF squared in the denominator. And what I'm going to do is I'm going to plot the relative sizes of these two terms. So this is the 1 over spectral signal to noise ratio. That's this effective Wiener constant. And this thing is the sum of the CTF squared. Now, here's why low frequency information is so important. This is a power spectrum. This is the signal to noise ratio as a function of spatial frequency of the original object. And you can see there's a huge amount, 1,000 times more spectral density at low frequencies than at high frequencies. And this is why being able to preserve the low spatial frequency components is so important, at least in finding a particle. You're going to need these higher frequency components for alignment and 3D reconstruction, but these low frequency components, which kind of arise in the general envelope of the molecule, these are much stronger. In fact, it's kind of interesting. This is comes from the shape of the molecule. Here's a little blip at alpha helical periodicity, 0.1 inverse angstroms. Here's the blip at hydrogen bond periodicity and the polypeptide chain at about 5 angstroms, and then here's higher frequency information. So anyway, so I'm going to watch these quantities accumulate. So here's the square of here are the CTF, individual CTF squared values. Because I'm doing this at a range of different defocus values, when I sum them together, I get something that doesn't oscillate quite as badly as the original CTF. And relative to the CTF squared, this K Wiener, this term, starts to get smaller. And as the red term gets relatively smaller, then we're getting closer and closer to doing a good deconvolution. So now I'm going to take it on and add a bunch more images, 10, 15, and so on. More and more images, and as we increase the number of images, this term grows, and that one remains the same, but relatively the contribution of this Wiener regularization term becomes smaller and smaller, and we get a better and better reproduction of the original. So what's happening is you can see as we proceed, we get higher and higher resolution points at which the terms in the denominator switch dominance. And we can see that happening also if we do a resolution measure. So this is the Fourier ring correlation. This is like the Fourier shell correlation in 3D. And we can see that as we accumulate more and more images, the resolution, which you could say is here at the 0.5 point, the resolution gets better and better as the signal from the particles overcomes the noise. Okay, is that cool? So this is restoring an original signal from a very noisy CTF modified set of images. Okay, so now we're ready to understand how a real reconstruction program works. This is FreeAlign. This is Nico Grigoriev's original CTF compensated reconstruction algorithm. And the way it works is this. We start with some initial guess of the volume. I'm not going to tell you how we get that, but we start with an initial estimate of the volume because this algorithm only tunes up, only refines the volume estimate. So we take the initial estimate of the volume, we compute a projection of it in a particular direction, phi sub I, and operate on that with the CTF for the ith image, and this is then a reference that is supposed to match the ith image. And so what we do is we vary this direction phi to find the reference image that maximizes the correlation coefficient for a given x sub I. So the correlation coefficient, remember, is the correlation between these two normalized. So once we have found the best correlating original image and reference, then we do the reconstruction, and here's how the reconstruction works. And what you're supposed to see is that this is just a Wiener filter. In the numerator, we have the data, but in this case, what it is it's a kind of Fourier slice reconstructed volume. We have the original image. We multiply by the CTF. Remember, that's just like the Wiener filter. We do a slice insertion. That's what this P transpose operator is, into a 3D volume, and we sum this over all of the images and all of the projection directions. So this is doing the 3D slice insertion to get some kind of 3D volume. In the denominator, we have again the CTF squared term, except that in this case, what we do is we take the CTF and insert it as a slice in a volume so that we kind of have two volumes that will be normalized. And we have a Wiener constant sitting out here. So, FreeAlign is just a Wiener filter that sort of operates on volumes. It operates on the Fourier volume where we have inserted slices from the individual images. Okay, you like that? Somebody tell me if you like that or not. And I apologize that you don't have the slides already. You will get all of these. Okay, so here's how FreeAlign works. You start with a preliminary structure. You find the projection angles that give the best match for each particle. And then you use that formula that I just showed you to produce a new 3D volume, and you iterate until you think that you've reached a good stationary point in the reconstruction. Now, FreeAlign now can also do so-called 3D classification. That is where you assume that your image can come from any of k different particle types. And our images are selected randomly from these volumes. We don't know which image came from which volume, but these are projected with noise added. And in that case, then, of course, we have different references that we have to work with. And what we do is it is at the same time we find the best projection angle, we also figure out which is the best volume that this matches. And so we can then do the 3D reconstruction just as before, just we do it for each volume using the particles that belong to that volume. So FreeAlign is really cool. It uses the Wiener filter, and the problem that it runs into or ran into in its early versions is that you have to assign a particular orientation to each particle image, and that makes a kind of sticky optimization where bad assignments early on remain bad later on. So more modern programs use maximum likelihood. So I'm going to tell you a little bit what likelihood is. So we're going to compare images in a different way. We're going to compare images by saying what is the probability that a given experimental image came from a particular reference. And the way we do it is we say, okay, let's suppose one pixel of our reference, the jth pixel, the actual value is here on this axis of possible pixel values. But we might, in our experimental image, pick values anywhere from this distribution. And I'm going to skip over the normalization part and just say that well, I can't skip over the normalization quite. So the probability that a given pixel is the same as the reference is just this Gaussian distribution. It's this exponential, and this is an important normalization. And this term turns out doesn't matter because we we're trying to find the maximum. We don't care about constants. And the probability of observing an entire image is then pixel by pixel. We subtract the two images, square them, sum them up, and make this Gaussian function out of it. And this is the probability of seeing our image given the reference. So all of the complexity in this formula comes from noise. Sigma is the standard deviation of the image noise. And so this is a very precise, or can be a very precise model of the noise in the images. Now, so that's the probability of an image. What's the likelihood anyway? So let's let big X here be our data set, our stack of particle images. And what we'd like to do is we'd like to maximize a probability. This is the probability of a volume given our data set. So we want to find the volume that maximizes this probability. Now, in statistics, Bayes' theorem says that the probability of the volume given the data is the same as the probability of the data given the volume times these two probabilities. P of V here is any prior information that we have about what kind of volume, what kind of set of voxels is more probable than another set of voxels. And this quantity, which is the probability of getting our particular data set, we're going to ignore it because we're not going to maximize over it. What we're going to do is maximize by varying V. And so what we're going to do, we're going to start out with the prior information, which is P of V. We're going to take our experimental data and compute something called the likelihood, which is this thing. And getting the product of these two then gives us the posterior probability, which we're going to maximize. So the likelihood is this backwards probability. It's the probability of the data set given the volume. But we say this is the likelihood of the volume. So the likelihood of the volume is this backwards probability, the probability of getting the data set from the volume. And what we're going to do is we're going to vary V to maximize this thing called the likelihood. So to get the likelihood, what we can do is we can compute we can compute this quantity. This is the probability of getting the image given the volume and the projection angle. And instead of picking the best projection angle, we're going to integrate this over all possible projection angles. So we start off knowing this guy. We know P of X given V and the projection angle. We're going to integrate it out. And then what we do is, because the noise in each individual particle image is independent, we can just multiply all of the probabilities together. And it turns out for numerical sanity, because this is multiplying lots of tiny, tiny numbers, we actually compute the log likelihood, where we just take the log of that. Let's see. Are you with me with this? I realize this is quick. Are you keeping up? Somebody do give me a thumbs down or not. Okay. So this is what we're trying to get, and we get it here by looking at the probability, assuming that we know what the projection angle is, but we don't. So we just integrate it out. This is what statisticians call marginalizing over the latent variable. Now, maximum likelihood is really cool because it's asymptotically unbiased. If the data set grows without bounds, then maximum likelihood converges to the right answer. At least that's what the statisticians tell us. Now, in order to efficiently maximize the likelihood, what we need is a probability of a particular projection direction. We'll use this function in a minute. So we see gamma sub I is the probability of the particular projection direction phi given a particle image and knowing what the volume is. And this thing is just a normalization of something that we already know. We already know how to compute this guy. It's this Gaussian distribution. So gamma sub I is the thing that Nico Grigoriev would maximize in free align, and he would just pick the best value. We're gonna keep all values of this probability of the projection direction. So here is the Relian refinement step. And what you're supposed to see is that this is just free align all over again. Remember, free align looks like this. We take the image, CTF, do a back projection, and sum that up. Here we go. We take an image, CTF, do the back projection. We weight it by this gamma function, and we integrate over all projection directions. So it's just like free align, except that we're taking a weighted average of the 3D slices resulting from the image with different projection directions. And the denominator uses a similar kind of normalization. Remember, free align had CTF squared. Here we have CTF squared, but we're again doing the integration over all phi values using this gamma function. There's also a fancier regularization term that Shores uses in Reliant. So when you're running Reliant or CryoSpark, the thing that takes the most time is evaluating this gamma sub I. Once you have that, then you can do this kind of iteration, and it works great. We can also do this to maximize multiple volumes simultaneously. We just make a fancier gamma function that includes the probability of coming from different volumes. Now, this evaluation of the gamma function is ridiculously expensive. So this is the orientation determination. This is the 3D reconstruction. N is the number of pixels on a side of each image, and big N is the number of images. And you can see that the really awful part is that finding the orientations goes as the 5th power of the number of pixels on a side of an image. T is the number of translations, and the number is huge. So if you put in a sort of typical problem, it's a huge number of operations, and with efficient programs, so like Reliant, it might be 1 CPU day to find the orientations for 1 iteration. Now with GPUs, this can be 100 times shorter. Now finding gamma is expensive, and this is just an example of trying to find one of the parameters, the in-plane rotation angle. So we have a whole bunch of references. There's an image. There's what that's the correct orientation of the image, and this is the correct value of the angle. And as we try different experimental images, sometimes we get totally the wrong answer for the maximum. So in order to not spend years evaluating the gamma function, both Reliant and CryoSpark use tricks to reduce the domain over which the integral is taken. That is, we find just a region of the five-dimensional phi space to evaluate. And the basic idea is let's do a low resolution estimate of gamma, taken at fewer points, and that's what this orange curve here is. Then we can look at the maxima of it. So the basic idea is based on our low resolution estimate of gamma, we say, well, it looks like we possibly could have a maximum of the high resolution gamma function in these places. And so we find this part of the domain where the true maximum is supposed to lie, and we only do our integration over this part. So here's a picture from Pujani's CryoSpark paper. This is what one would do as far as finding the best orientation over all values of the tilt and the spin on the axis of the particle. And what they do is at low resolution, they try to find the best point and possibly best regions. Then select just the most promising regions of the search space, and then in another iteration, they reduce the search space much smaller. And so by being very clever and choosing where to look in the space of so many different orientations, these programs, especially CryoSpark, is extremely efficient. I wanted to mention one other cool algorithm, which is stochastic gradient descent. Here's the basic problem. We're trying to maximize the likelihood. So we start with some kind of random initialization of our iterative refinement algorithm, and we start increasing the likelihood, and we get to a maximum of the likelihood, but the maximum is the wrong structure because we're way away from where the real structure ought to be. So the idea of stochastic gradient descent is instead of computing the likelihood on your entire data set, we're going to pick one random subset of the images and take a step, and then we'll take another random subset and we'll take another step. And so the idea is we start with our terrible origin and we take these random steps, and the randomness helps us sample a larger region of space of all 3D structures, and so converge more reliably to the true structure. And this SGD is the way one can get an initial model from a truly random initialization. Okay. Well, I told you about 3D reconstruction, but it's exactly the same algorithm. And in fact, Reliant uses literally the same program to do classification and refinement in 3D and 2D. Okay, I'm over time, but that's what I wanted to tell you.